Hi, my name is Lena, and together with my colleague Ragav, we did the exercise 1 for ubiquitous computing in winter semester 2024. For reference, all of the following exercises were completed using the ESP32 microprocessor. For the first task, we were asked to connect the 3.3 volt supply to a resistor and an LED to make the LED light up and subsequently calculate the voltage drop on both the resistor and the LED. Once we assumed the typical forward voltage drop for an LED around 2 volts, this was quite an easy calculation because we know that the total voltage drop in the circuit has to accumulate to the source voltage, which is going to be 3.3 volts. So after assuming a 2 volt and measuring the 2 volt voltage drop on the LED, we were able to quickly deduce the 1.3 volt drop on the resistor. Experimentally, this is how that turned out. Here you can see the video of my project partner doing the measurements with the multimeter. We ended up having slight deviations from we expected theoretically. So we ended up having around 1.4 volt drop on the resistor, which is a 0.1 deviation from what we expected to see. So if you remember from the previous slide, we expected 1.3. And the total voltage drop on the LED was around 2.04, which is around where we expected the results to be. From this, we can deduce that there is a bit more than a 3.3 volt coming from the source, which we will also prove in the next tasks. For task number 2, we were asked to connect 2 resistors in series with the same 3.3 volt power supply and to calculate the voltage drop on one of them. So given that we tied 2 resistors with the same 220 ohm resistance, it's very easy to sort of deduce the expected value, which was going to be just 3.3 volts divided by 2, because we know that the sum of those voltage drops need to equal to the voltage of the source. But we supported also this claim by doing a bit more calculations. So we were able to calculate the current in our circuits, which is going to amount for 7.5 milliamperes, and subsequently calculate the voltage drop in one of the resistors. And again, we come to the value, which is around 1.65 volts. So here you will see how we come to that value experimentally. Here you will see my partner come to the 1.7 voltage drop on one of the resistors. So if you remember from the previous slide, this is a slight increase of 0.05 volts from what we expected it to be. There are multiple reasons that could cause this deviation between the experimental and the theoretical value, but the two ones that we chose that are the most likely are the following. So first of all, we know that all the resistors that we use have a certain tolerance level, and the particular one that we used has a plus minus 5% tolerance level. And this measurement sort of falls within that scope of 5%. So the 0.05 deviation that we have from the expected value falls within this 5% deviation. And second of all, what could be the case is that simply the power supply may vary from 3.3 volts. And this is something that we also observed previously, that simply that there is a bit more than 3.3 volts coming from the power supply. So for the third task, we were asked to connect 2 resistors in parallel and without a power supply, and to calculate their equivalent resistance in theory and compare it to the experimental value. So we know that 2 resistors tied in parallel have equivalent resistance with the following formula that we see on the slide. From there, we were able to very quickly calculate the equivalent resistance, which we expected to be 110 ohms. In practice, we were able to measure the equivalent resistance of 112 ohms, which again falls within the scope of plus minus 5% deviation that we expected from the resistors that we used. And finally, for the digital input-output exercise, we were able to make 2 different LEDs, a green and a red one, blink interchangeably, and here provided is the code that we used to make that happen. Thank you very much for your attention.